So good morning everyone. Today we are going to introduce the explicit treatment of the configuration space. Okay, so last time we saw how to deal with parametric manifolds or parametric surfaces or parametric spaces, whatever you want to call it. And today, we advertised or kind of hinted that configuration spaces are actually going to be such. So today, what I want to do is to properly define the configuration space from useful Newtonian classical mechanics, and hopefully give you intuition of what generalized coordinates, which will play the role of our parameters q1, qn last time in classical mechanics, in Lagrange and Hamiltonian mechanics. So, first of all, as we said last time, analytic mechanics is concerned with motion of particles is somehow restricted, or could be somehow restricted in general. So, the key idea about the configuration manifold is that it represents the geometric space of all possible parameters, or all possible values of parameters that identify uniquely one state of the system, of the mechanical system. In our case, a state of the mechanical system is fully identified with the position of the particles that compound this system. Right? So in advance, masses of the particles will be given, and constraints on where and how they move will be given, and now the only thing that's left for us to understand is how these particles move in the possible spaces that they are restricted to live in. So, this is the basic idea. So I think the safest way to actually do this is to work some examples and see how we identify uniquely the position of some mechanical system, some concrete mechanical system. So let's imagine the simplest case possible. So first of all, consider three-dimensional Euclidean space of usual Newtonian mechanics, and consider a particle that is moving freely, in this case, potentially freely. There may be potentials and forces acting on it, but in principle, it could be everywhere. That's the thing. It could be everywhere. It could get to every single point of the space. So, how many independent parameters do we need to identify at this point? Well, usually in Newtonian mechanics, we describe the position of this particle by picking an origin and using a position vector x, which, you know, with projections means x, y, and z, right? But this is a very good choice for coordinates, and indeed a very useful one in general. But we could use a different set of parameters. For instance, we could use cylindrical coordinates. We could have a cylinder, you know how to deal with cylindrical coordinates, right? You have a cylinder like this. You take this radius rho, this height theta, and if you project here, you have an angle phi, and you take, and then we can also identify the point with theta phi z. Sorry, rho phi z. Okay? So that's another option. Another option, of course, spherical coordinates, or indeed any set of coordinates of a generic point in 3 dimensions. So, in our case, of course, the choice of coordinates will be completely arbitrary and up to convenience, I'd say, because it's quite not important for the actual behavior of the system. It might be convenient to pick one coordinate system or another, given specific symmetries of your system, of your interactions. So, for instance, if there are a force that is central, then it's very, very useful to use spherical coordinates, because then it means that the force lies on the radial direction, and it's it's much nicer if there's some sort of rotation in the system, then cylindrical coordinates around the axis of rotation may be really useful to be used as well. But there are many considerations that one can have in mind when is about to choose a coordinate system, but that's not our problem. That's not what we care about. What we care about is that we need 3 of them. And indeed, in order to represent an arbitrary, completely arbitrary point of the particle could be, where a particle could be, so it could be that one, could be this one, could be this one, could be this one, could be that one, could be that one, could be that one, could be that one. It could be the whole R3. Then we say that we need a map from, and this is why I call this E3 and not R3, otherwise it's quite redundant. That's what we need, a map from R3, or a subset of R3. For instance, if we use cylindrical coordinates, we see that rho only needs to be positive, and phi only needs to be between 0 and 2 pi, so, and theta needs to be real. But these two arbitrary. So in general, will be, let me call it U, the subset U of R3 into E3. So in general, regardless which particular choice of coordinates would be, these should be 3 of them, and we call them Q1, Q2, Q3. Okay, and then this gives us x of 1, 2, 3, wherever. Okay, so for instance, in Cartesian coordinates, Q1 equals x, Q2, not equals, but identically equals y, because meaning in this case Q1 is what we call x, in this case Q2 is what we call y, etc. And then similarly for that, Q1 is rho, Q2 is phi, etc. You know about it. So this is the particular case in which the particle could be everywhere in R3, so we just need a general coordinate chart or coordinate system on R3, and that's a valid set of generalized coordinates or parameters. So what is Q in this setting? Well, Q, remember from last time, I'm going to stress this again, is the geometric space that is the image of all possible generalized coordinates. Okay? So, for instance, so it's really easy to see what Q is in this case, because this is just a general coordinate system of R3, sorry, of E3, so obviously Q is just E3, the whole three-dimensional space, as we expected. Because so what was the consideration for us to start defining these generalized coordinates? Well, it was that the particle could be anywhere in E3, and so anywhere in E3 means that we can use an arbitrary coordinate system on E3, and that's a valid parameterization of our possible configuration space. A particular configuration is a particular position of the particle at that point. And since we are considering a model in which particles are just points, then that means that a particular configuration is uniquely given by a set of coordinates. So that is a set that is given by this map, phi, Q1, Q2, Q3, and we normally omit this because we assume that this is a map of this kind. Remember that we said last time, this lives in a parameter space which is just a subset of R3, and this would be, in general, a subset of the geometric space of E3 or some bigger dimensional space. Okay? So this is in our example. Okay, so in our example, Q. So let me summary Q. In our case, is E3. It's three-dimensional Euclidean space. Okay. Many times you will see, for practical purposes, that Q is actually R3, but in our purposes, in our discussion, this E3, for us to see that it's a geometric space. Okay, let's consider another simple example of a mechanical system. So imagine that we have a wire, so a metal wire on space, given by a specific curve that we know already. It's given, it's fixed in space, you know, it's tightly grounded in some wall, or and so yeah, so we have three-dimensional space, and we have a wire. It's just a given curve, fixed, completely, with infinite mass or infinite forces fixing it in space. There's no way it is going to move. And then we have a bead. A bead is just, small marble with a hole in it, so that we can fit through this, and so you can move. Right. So you can move around, reach around. Okay. So in principle, of course, we don't care about which forces will act on this. We could have a gravity field. We could have it could be charged, and then we could be magnetic and electric fields. We don't care about that. We just care about how we describe where it is. So now, this goes to infinity. Okay. So, no, it doesn't go to infinity. It actually ends at some point. Okay, can't go further, and this ends at some point. We go to infinity, there's no problem with that, but this is more concrete, so we can actually see the whole space. So, let's see what a bead looks like. Okay. So, in this case, we want to ask the same question. So, how do we identify an arbitrary configuration? So, what is a configuration? Again, a configuration is all possible positions of all the particles of our system. In our case, we just have one particle. Okay, this is three-dimensional Euclidean space or geometric, and it lies on a line, so it's restricted to live there. So, of course, intuitively you already see what the configuration. So conceptually, you already see what the configuration space is. So this thing, you have it already in your mind. So what are the possible places that this bead could be in? So obviously, this one, at the very end again, or that one, or this one. Okay, so the possible positions of this bead, this particle, could be anywhere along this wire, this line. Okay, so you say, okay, so how many parameters you need? Well, it's obvious that you only need one, because a curve is obviously parameterized by one parameter, but not any. I mean, if you want to define parameters from three-dimensional geometry, not any parameter will do. So, for instance, if you say, let's take the height of this particle to the set, right? You want. So, well, let's try this. So, we already know from obvious geometric. From the obvious geometric fact that this is a line, that we will just need one parameter, right? Because it's living on a line. So our parameter map would be some subset of R into R3. Okay? So we just need one Q1 and Q1. But it's very important that you pick parameters such that they uniquely determine a position. So, such that every different single value of a parameter actually represents a different point of the system. And hence, it would, for instance, try to pick the set component of this Cartesian frame, of this particle. That will fail to be a unique parameter, because, for instance, if we see this as being horizontal, every single configuration that corresponds to the particle being in any of these positions correspond to the same set, so it projects to the same set there. So it's not okay, or if this goes up, there might be two different points, here and here, in which two different points have the same set. So that is not a valid parameter. So there's a very natural parameter that you could pick, and that's the length of the wire from an arbitrary point, say this end or that end or wherever. So for instance, from this end, you take this, take that. Okay, so this distance, call it S, is a valid Q because it's unique. I mean, it's always positive, it's zero there, and it's always growing by definition of distance, right? It's always growing along it, so it's a unique parameterization of the curve. Of course, you know that this is what is called a affine parameter or natural parameter of the curve, obviously. So obviously, any other parameter that you multiply this with something, add something, wherever, will be a valid Q, a valid Q1 as well, okay? So, let me call the wire, say, W, okay? As a subset of E3, it ends here and here. And let's say that we take the length from this end. So say that the total length is W. So you say that the total length of this, so the length of the wire is W from wire. Then we see that with this particular choice of Q1, then what is Q? Well, is all possible values of this map when Q1 is S, or all possible S. Since S goes from 0 to W, so in this case is the image of the interval 0 to W. I mean, this is very kind of obvious and tautological. I'm just making it explicit for you to have feeling, but obviously we have the map from distance 0 to distance, the whole distance, so obviously this is W. Q, in our case, is all this possible position. And so this is Q, this is the answer. And remember, we're just trying to make different examples for you to see what configuration space is and how we pick parameters on this configuration space. So how do we so for instance here, configuration parameter space was just numbers, so sorry, 3 numbers, so 3 coordinates. In this case, configuration space is just the value, sorry, R 0 W. Okay, so this is our configuration space, and it maps there, right? So this is our parameter space. So okay, this is what we call all possible Q1s. In this case, it's all possible S. And this is where it maps. So the image of this is the whole wire. So Q, in this case, is a wire. Okay? So you might say, okay, this is obvious, this is really easy. But you're always, okay, so the particle is limited to move along some submanifold, along some space, and so it's always the case that the configuration manifold is that space. That's true when we're talking about one particle, but let me simply add another particle to this system and consider a new system. So let me update this. Which is, okay, is bad parameter, that's a bad parameter. Okay, so consider the exact same system. And now consider 2 different particles. Let's take 2 different particles. We have one particle here. Right. And say we have one particle here. So we have these particles, two particles. I mean, each of them will have a different mass. And let's say we pick the same sort of parameter, which is just the distance, so the length of the curve. And let me call it times this an arbitrary number or whatever. So let me call it, this is Q1, this position Q2. Oops. Right. So in this case, to fully determine the position of the configuration of the system, this is why configuration is a word useful. I mean, why we use configuration space and not position space. Because if we have more than one particle, we have more than one position. We have a position for each particle, but configuration means the set of all possible positions of the whole set of particles of the system. So in this case, a configuration of this system is this photography. So we have this kind of slide of time. If this evolves, this could move there and there, and so we have a different one. So we can have this here, this here, this here, this here, this here, and we can have this here, this here, this one here, okay? And so each pair of two positions is a configuration of the system, right? Okay, so in this case, to fully determine the position of the system, we need two parameters. Say, two numbers that indicate the length of the wire up to the position where they are, right? So we have a map in general, so we know that it's going to be two numbers, and we will construct a particular parameter space now. We know that it needs to be two parameters into E3. Okay. And so in our construction, in our particular construction, we have Q2 and Q1, right? And it gives me position, wherever it is. Sorry. And it gives me, I mean, that is not entirely true. So now we see that there's something funny going on with the definition of this thing. I mean, being always mapping into E3, right? Because now these two things are not mapped to a single point of E3. One is, and the other one is as well. But the two of them together, they're not mapped into one single point, because this is a point, I mean, this gets mapped to one point of E3, and this gets mapped to another point of E3. So together, these get mapped into two possible, I mean, in general, two possible positions of E3, because there we have two particles. I mean, this is, if we take the general case in which one particle is described by one E3, two particles is described by the Cartesian product. And, you know, Cartesian product is just all the combinations between the two, right? So, so you could have, gets mapped to the position of the first one and the position of the second one, okay? Okay, like that. Anyway, so the thing is that we don't really care about this. We don't really care about this because this may be complicated. I mean, not complicated, really high dimensional. I mean, in this case, it's already 6-dimensional. And imagine that we just have like 20 particles there. That would be simply 6-dimensional. So we don't really care about this space, or moreover, we don't really care how the image of this, which is actually a configuration space, leaves. But in our case, I'm going to be explicit. The image of all possible Q's is a subset of a 6-dimensional Euclidean space, right? So you see, this is by definition, of course, And so you see why this gets complicated, and you see why this is a useful notion to have in mind abstractly. And we don't care about if it's a set manifold of some higher dimensional space. We just care about we just care about how many parameters we need to identify different positions of the particles that compose the system, and how many particles there are, so that we have a family of parameters, in this case Q1 and Q2, because it's the simplest one-dimensional case, in which the position, the configuration of the system is fully determined by Q1, Q2, and in this case, you know, Q1, so Q1 and Q2, these each belong to, recall that full length is value to the real interval, like that. And so effectively, our parameter space, so parameter space is just a square. So we have 0, W there, W there. Okay, so we have a picture, yes, and so this is not mapping to this E3 space. This is mapping to the E3 space times E3 space that compone all these possible particles. Okay, and so the image is a subset of this. So in some sense, the image of this, by phi, is in some sense one wire times another wire. Okay, so this is actually a two-dimensional manifold. It's a one-dimensional manifold, Cartesian product, another one-dimensional manifold, but they live in a six-dimensional space. So we don't really care about where these manifold lives. We just care about finding a good parameterization of the positions of all particles, and doing so for every single particle of the system. And so we have a proper family of parameters, or generalized coordinates. This is the name that we normally use for them, and so that we can faithfully represent every single point of the manifold. So I hope this is clear enough for you to just go ahead and try and find complete sets of parameters that identify uniquely the configuration of your system. And I hope that it also allows you to conceptually just make the leap of saying, well, I don't care about, well, sorry, it's not that you don't care about that, it's that once, I've assumed that I've found a valid parameterization of my space, of my configuration space, and so from now on I can discuss very general mechanics just by saying, let's a configuration space parameterized by n parameters, such that we normally, again, remember that the set of all possible parameters is parameter space. It's not configuration space, but it uniquely identifies every single point or every single element of the configuration space. So many times, by abuse of notation, just dropping these parentheses and this letter, we could write that. So this is indeed true. In any case, that's true. But not completely equals, but it's true that it's isomorphic with all possible sets. Here, sorry, let me write that in red. So it's our final conclusion. Many times we just say that the configuration space is the space of all possible parameters. It's not quite true, so it's actually isomorphic to that. But since the actual configuration space lives in a very high, potentially very high dimensional Cartesian product of E3s, but we don't care about that. We just care about if we construct it properly, then this is isomorphic, so we have a bijection between the two, as we see here. I mean, there's a bijection between points of length 1, length 2, and possible pairs of positions of these particles, because it's just a length 1, that's where the first particle is, length 2, I mean, you see. I mean, this is a bit explicit, but, you know, that is Q1, that is Q2, so you read Q1, that's where the first particle is, you read Q2, that's where the second particle is, and so you see that, and since they range from 0 to W, the whole length, you see that this whole square is isomorphic to all possible configurations of the system, right? So this is the basic idea of the configuration space. So I picked these examples because they are easy enough to draw and to actually compute explicitly, completely. So you could actually get a feeling of what's going on. But I hope that you see that this is just a very standard procedure that it's nothing to do with the dimensions of the space that we're dealing with. You just need to care about that the map that you construct is isomorphic. Okay, so that's basically the idea of a configuration space. Remember that this identification is quite useful, although conceptually is very useful to distinguish between parameter space of Q's or generalized coordinate space and the actual configuration space. Okay, I mean, it's obvious that a particle moving in three-dimensional clear space is not just three numbers. More, I mean, quite obviously, because the choice of three numbers is completely arbitrary and only depends on what coordinates you pick. Whereas the phenomena of a particle moving in a three-dimensional space is something completely unique and fully well defined, uniquely, right? So this is the idea. So from now on, we will just consider our configuration space to be a parameter manifold, you know, in which the parameters Q1 and Qn fully identify uniquely all possible configurations of our system. And here's an example, a trivial example of what a configuration is for one particle, and this is a simple example of what it is, a configuration, what a configuration is for many particles, or many particle system. Okay? So you see that the treatment is absolutely equivalent. I mean, I call it Q1, Q2 here as well, Q1, Q2, and the only difference is that this comes from one particle and is living in a bigger dimensional space, and this comes from more particles living in a more restricted, lower dimensional spaces. But the treatment is absolutely equivalent because it fully determines the mechanical state of the system, that is, where they are. Okay? Not the mechanical, the configuration of the state of the system, which is the information telling you where each particle is in the possible places in space. Okay, so next time we'll do tangent bundle and cotangent bundle, and I hope that you enjoy it. And